So we got an introduction to exponential functions, and we can now use this to deal with models in real life. In real life situations, the graph or the certain function of exponential is really similar to what really happens when stuff increases or decreases. It's a very useful function to use when modeling real life situations. So let's look at this one here. The number of people infected with the disease is modeled by the formula n is 300 minus 100 e to the negative 0.5t, where n is the number of people infected with all the disease and t is the time in years after detection. How many people were first diagnosed? Well, when they were first diagnosed, it'll be when t is equal to 0, right? So all you need to do is plug in t0 into this n equation. So n will be 300 minus 100 e to the negative 0.5 times 0, which is e to the negative 0. Anything to the power of 0 is just 1, right? So this would be 300 minus 100. So initially there'd be 200 people who were infected. What is the long-term prediction of how this disease will spread? Long-term just means what happens when t gets very, very large, i.e. when t will go to infinity. This means that 100 e to the minus infinity will tend to actually be 0, okay? And so therefore n will be 300. So after a while, n will tend to 300. If you're unsure about this kind of stuff, what you can try and do is try and sketch the graph 100 e to the minus infinity, or 100 e to the minus x, okay? For minus x, right, if it's e to the minus x, we know we reflect it in the line like this, and now it's going to look something like this, right? This is going to be a graph for 100 e to the minus x, where this is 100. And as you can see, as x gets very large, this would tend to, or it will become very, very close to 0. That's why we say it tends to 0, and that's how we get n is at 300. So if you're unsure about like tending to stuff, like tending to infinity, tending to negative infinity, maybe just sketch the graph yourselves and you'll see it. C, sketch the graph of n against t for when t is larger than 0. So n was 300 minus 100 e to the negative 0.5t. So it's just basically graph transformations. So initially, if it's negative, right, we flip it. So 100 will look something like this, right? But there's a minus in front, so now this graph will flip upside down. So now this will flip in the x-axis, going like here. But now this is negative 100. And we're adding this plus 300, so all the graph is going to move up by 300, right? So now, originally this was the asymptote here, right? So now the asymptote will be at 300. And the graph will look something like this, where this point here will be 200, right? Because 100 plus 3, minus 100 plus 300 is 200. And this would be the graph for this certain equation. And as you can see, as t gets large, it will tend to this n is 300. So we know part B was correct just by looking at this graph here. All right, let's try another one here. So we have Nigel, which has bought a tractor for £20,000. He wants to model the depreciation of value of his tractor t pounds in t years. His friend suggests two models. So the tractor is going to depreciate in value, and he's trying to work out the depreciation rate with two different models. Use both models to predict the value of the tractor after 1 year. So after 1 year, you just have to plug in t1 to each model. So model number 1, t is going to be 20,000 times e to the minus 0.24 times 1. And model number 2, same thing, t is 19,000 e to the minus 0.255 times 1 plus 1,000. And you just have to find these values by just plugging into the calculator. Right, use both models to predict the values of the tractor after 10 years. Same thing for part B. Now we just plug in t is 10 to each model, okay? And then we compare the values for each one. If you were to do that, you'll get that model number 1, you get a value of £1,814. Model number 2, you get a value of £2,483. Okay, just plugging in the value t is 10. Sketch a graph of t against t for both models. So it's about sketching again. So model number 1, let's do that first. The t equation was 20,000 e to the negative 0.24t. So if I was to sketch that, we'll start off at 20,000 and then we'll go down like this to here. This value here will be 20,000 and it will go down to 0 as t increases. Right, model number 2. So the t equation for the model number 2 will be equal to 19,000 e to the negative 0.255t plus 1,000 like this. Okay, so it's got a number of different transformations, right? So first things first, let's deal with each transformation first. So this negative means, right, we just flip it. So the shape is going to be flipped and it's going to be times by 19,000. So it's going to be like here. But this value is going to be 19,000 like this. So yeah, 19,000. We're now going to add 1,000, meaning the whole graph is going to move up by 1,000, right? Including the asymptote. So if I was to sketch it again, the asymptote now will be at when the capital T is at 1,000. The shape will be similar like this. And now when it's going to cross at 20,000. Like so, okay? And so this would be the shape of this second model's graph. So as you can see, you just have to be very careful with the transformations occurring to the exponential graph. And part D, interpret the meaning of the 1,000 in model number 2 and suggest why this might make model number 2 more realistic. So if you just look at these two graphs, right, if you see as t gets very large, the first graph will suggest that the value of the tractor will become 0, right, because it's going to go on forever until it reaches 0. Whereas the second model, it suggests that as t gets large, the minimum value will ever be will be £1,000. This would be a bit more realistic because we're talking about the price of a tractor, right? And no matter how old the tractor gets, you can always get money for like metal costs of the tractor or just like the parts of the tractor. So it will never actually be 0. So this model number 2 will probably be a more suitable model for calculating the depreciation.